Hello, my name is Jihu, and today I'll be presenting selective feature sampling for privacy-preserving and communication-efficient federated learning in medical AI. This research focuses on improving communication efficiency and privacy in medical federated learning systems where data sensitivity and transmission costs are major challenges. In recent years, medical AI has grown rapidly, but real deployment is still limited due to strict privacy regulations and concerns about data sharing. Centralized AI systems often require sending raw data or full gradients, which leads to both privacy risks and high communication overhead. Systems such as MAI DXO from Microsoft show strong diagnostic performance, but are difficult to scale securely due to these constraints. So, the goal of this research is to design a federated learning method that significantly reduces communication while minimizing exposure of sensitive representations. However, in traditional federated learning systems, it has three major issues. First, it suffers from large communication overhead because each client must transmit full model updates each round. Secondly, many updates are redundant and low value, which slows training processes. And third, gradients can leak private information, posing privacy risks. These three major limitations motivated the development of a more selective and efficient approach. The core idea of SFSFL is simple. Instead of transmitting the entire model update, we only send the most informative features. This idea is inspired by feature selection and few-shot learning, where small but meaningful representations could be used as highly effective processes. By doing so, we achieve three major benefits. Firstly, significantly reduced communication. Secondly, maintained or even improved accuracy. And third, reduced risk of leaking sensitive gradients. SFSFL works in these three major steps. Firstly, each client computes the importance of local feature representations. We experimented with gradient norm, attention values, and mutual information. Secondly, the client selects only the top K important features instead of full gradients. And finally, these compact feature updates replace the full model update during communication. This formula here shows how feature importance is measured using gradient magnitude. And overall, we transmit far less data without sacrificing meaningful information. This slide illustrates the entire architecture. Clients locally train their model on private data, compute feature importance, and then sample the most relevant features. Only the selected features are sent to the server where aggregation and iterative refinement can occur. This pipeline preserves privacy, reduces bandwidth, and maintains a global learning quality even in heterogeneous environments. As for our experimental setup, we used the chest X-ray 14 dataset. And to create a realistic federated environment, we split data into 10 clients following patient IDs, which naturally introduces non-IID distributions. We used a ResNet 18 backbone pre-trained on ImageNet, and training was performed for 50 communication rounds with 5 local epochs each. All experiments were run on an RTX 3090 using PyTorch. Here are more specific details about the dataset and the federated setting. The chest X-ray 14 dataset contained around 112,120 chest X-ray images with 14 disease labels in a multi-label setting, and it shows strong class imbalance similar to real clinical data. The data is partitioned into 10 clients based on patient IDs, so each client roughly corresponds to a different hospital. The stacked bar chart on this slide visualizes the label distribution of all 14 diseases across the 10 clients. Each bar represents one client, and each color segment represents a different disease label. As you can see, some clients are dominated by certain diseases, while others have very different proportions. This clearly illustrates a non-IID heterogeneous client distribution, which makes the federated learning problem more challenging and is a realistic setting for medical AI. These tables summarize the main results. Communication was reduced from 11.7 megabytes to just 2.4 megabytes per round, which is around a 79.5% reduction. And despite sending far less information, accuracy actually improved from 78.7% to 81.1%. This demonstrates that selective feature transmission not only reduces bandwidth, but also leads to stronger generalization by reducing these noisy updates. But why does communication decrease so much? This is because SFSFL replaces full gradient transmissions with only top K important features. And since only a small subset of meaningful representations is sent, communication remains minimal at every round, regardless of the training progress. This structural reduction makes the method ideal for bandwidth limited environments, especially in medical institutions with largely restricted connectivity. Now we also compare three methods of importance scoring, which are firstly gradient norm, secondly attention-based scoring, and thirdly mutual information. Gradient norm performed the best because it directly reflected the loss landscape and it achieved the highest validation accuracy of 81.1% and showed the most stable conversions. Attention-based scoring and mutual information were still valid but more sensitive to non-IID noise. The next experiment, the next experiment analyzed stability and convergence speed. At 20% sampling, the model achieved the lowest variance and the most stable training curve. On the other hand, ratios below 5% led to unstable updates because too many important features were discarded. And in terms of convergence, 20% also reached the target accuracy the fastest, outperforming the rest of the percentages, which were 10%, 5%, and 2%. These two graphs show the trade-off between accuracy and communication under different sampling ratios. The accuracy curve shows that 20% consistently performs the best across all rounds. Meanwhile, the communication plot shows a dramatic reduction even at 20%, with diminishing returns at lower ratios such as 5 or 2%. This confirms that 20% is the optimal balance between performance and efficiency. So in summary, the experimental results demonstrate that SFSFL achieves a substantially large communication reduction, which is approximately 80%, while maintaining or even improving model accuracy. The selective transmission of high-value feature representations enables more stable and more robust aggregation under non-IID client distributions. These characters indicate that SFSFL is highly suitable for real-world medical federated learning scenarios, particularly in multi-institutional settings where privacy protection, limited bandwidth, and deployment scalability are essential requirements. Now, to conclude, this work introduces a simple but powerful idea called selective feature sampling, which enables communication efficient and privacy preserving federated learning. We achieved large bandwidth reductions, improved accuracy, and stable convergence with gradient-based sampling. These results show strong potential for real-world medical AI applications where data sharing is largely restricted. Future directions include integrating stronger privacy protections such as differential privacy and secure MPC, extending SFSFL to larger models and more transformer-based architectures, evaluating performance on real multi-institution datasets, and also developing adaptive sampling strategies that adjust to client heterogeneity. That is the end of my presentation, and thank you so much for listening.